Alright, hello everyone, this is Mr. Crozier. I'm going to go over AP problem set number 5. Well, problem number 1 is just our old-fashioned way to find the derivative. You should notice that this means take the derivative. So if I take the derivative of this, it's just 2x. But the long way to get to 2x is to do all of this work, and that's what you're asked to do on this problem. So it's kind of like finding the derivative before you know the power rule. Number 2 is the same thing. You're finding the derivative, but you're plugging in 6. So the derivative is 2x, plug in 6 is 12. But again, this is what we had to do before we learned the power rule. So make sure you remember that. Make sure you recognize that this is simply asking for this, because you may get asked that on the test. You may get asked, what is this? And instead of going through the work, you just know what it is supposed to be. Number 2, we have a formula. It is a related rates. Well, if you take the derivative with respect to time, you'll have dv dt is 4 pi r squared dr. Plug in everything you know. Solve for this dr dt. Here's the stuff you know. Number 4, maximization problem. A number plus 3 times a number is 12, and we want to max these products. Well, if I solve for 1 here, I can take this x and put that right there, and now I have an equation with just y. I can multiply that together, find the critical point. Critical point is when the derivative is equal to 0. Then I'll be able to find out my numbers. The limit, 3 from the left side, the smaller side, so that means I'm just using this, and I can just use direct substitution there. Number 6, a farmer's field. Well, there's the field, x, and y. He has 400 fencing, and he wants to max the area. Well, area is x times y. Again, if you solve this one for y, you can plug it in there, and now I have an equation with one variable. I can distribute it, set the derivative equal to 0. I'll find that maximum point. It's the extreme value theorem. Where is the derivative equal to 0? I have my 2 points. Down at the bottom, the function. What's the limit as I go to 3? Well, it's going to 1. What's the limit at 4 from the greater side? Well, that's up here at 3. What's f of 2? Nothing. What's f of 3? It's right there at 2. What's the limit at 4? Well, the limit doesn't exist because the points don't come together. What's the value of x to the 1/2? Well, 1/2 is right there. I said it's about 1.6. All right, page 2. Horizontal tangents. Well, horizontal tangents are where the slope is 0. So take the derivative, set it equal to 0. Here's the solutions, 1, 2, 3 points. I plugged them in the original to get the point back. Particle moves. Where is it at rest? Well, that's a horizontal tangent again. I want the derivative to be equal to 0. Left d right plus right d left. Solve it. I factored out this. This factor will never be 0, but this will be 0. If you remember this trig equation from last year, I could subtract the cosine over, divide by cosine, sine divided by cosine's tangent. When's tangent -1? Here and here. It's a tricky way to solve that equation, but hopefully you remember that from last year. Second derivative, that's what that notation means. It's a little bit weird, but it just means take the derivative once, take it twice. One of our favorite problems, equation of a tangent line. Take the derivative, plug in 2, that's your slope. Once you have the slope, plug in the point. Where did I get the 5? From the equation. 2, 5 is my point, 2, 5, 13's b here. If you wanted to do it another way, you could say this is y minus 5 is equal to -4 x minus 2. That's another version, which will leave you to right there. Same thing. Related rates problem here. They're tricky at first, but once you figure them out, they're not too bad actually. Draw a picture. A ladder is 50, and it is moving that way and this way because it's sliding down the wall. The ladder's falling down and moving that way. The x change is 3 at the point 30, 40 is what we're talking about. You get that from Pythagorean theorem. The variables are x and y. These are a specific point. So the formula of the situation is x squared plus y squared is 50 squared. A squared plus b squared is c squared. You don't use these because these are variables. These are changing. So we use x and y. Take the derivative with respect to t. 2x dx dt, 2y dy dt, 0. Plug in everything you know. 2 times x times 3 is 180. 2 times y is 80. dy is unknown. Subtract it over, divide it over, negative 2.25. This is changing, and this is changing. This is changing 3 that way. This is changing down, negative 2. 3 trapezoids, 1, 2, 3, 1/2, height, which is actually kind of like the width on this one, but height if you turn your paper that way, and then you add the bases. I estimated some 29.6. We have a bunch of integrals here. I kind of drew a picture to relate these. The first one says from -5 to -1, the area is 4. -5 to 1, the area is 4 right there. From 3 to 5, it's 9. 3 to 5 is 9. And then they tell you the whole thing is 10, so I wrote that up here. Now the first question you're asked is, what is the area from -1 to 3? Well, look what I have here. I have 10 here and 13 already, so this had to be -3 to make it equal to 10, right? I had 4 plus 9 plus something had to be 10. Well, that's a -3. And then once I have that, I can answer the rest of the question. Well, what is this one from 3 to 5? Well, I have that, right? No, I have 3 to 5. This is asking from 5 to 3. It's just a negative value. And from -1 to 5, -1 to 5, that's 9, and -3 is 6. If you draw a picture like that, probably the best way to get there. Some problems we really haven't done, they're new ones here. It's just a weird little formula. I have a function for h, and f is its inverse, meaning this equation was y equals 7 minus x minus 2x to the 5th. If I do an inverse, it means I switch the x's and y's. And now I'm asked to find a value here for this function, and this is f over here. This is my f of x function. Imagine trying to take the derivative of this, or solving this and trying to figure out stuff. It's going to be very complicated. So we have this formula that just says if I want the derivative of f, which is here, all I have to do is do 1 over the f of x value, and I have this point on here. If I figured out this point, if you plug in -1, you get 10. So if you switch that, if you plug in 10, you get -1 here. You just use that to figure this out. So I have 1 over f of 10, which is -1, and all I have to do is take 1 over the derivative of this. And usually this derivative is a lot easier to do. So I took this derivative here, and it comes out to be -1 minus 10 x to the 4th. I can plug that in and I get -1, -111. Same thing here. I have a function and I'm looking for its inverse. Well, g of 1 is 4. If I plug in 1, I get 4. So in the h function, since it's the inverse, if I plug in 4, I get 1. Then I can just go through these steps. Sorry, this is supposed to be a 4 here. I'm doing a 4. So I take the value here and I plug in my 1. Because I have 1 here, and now I just plug in 1. Sorry, that should have been a positive 1. I did have different numbers earlier. I plug in a 1, and I have 1/8. Just if you can remember this formula, it'll make it a lot easier for you. Alright, number 17, we have the inverse function here, and the formula is here. I looked it up at one of the derivative formulas. The derivative of inverse sine is the chain rule over the root 1 minus u squared. So it's the derivative of this is 3, it goes on top. It's always 1 minus that square. Just a memorization rule. There's a proof for it, but we never studied the proof. It's just one of those you want to memorize. Alright, we have a function here, and we're going to use the equation of the tangent line and plug in 7. That's what it means to approximate this. So we have to go through our regular work to find the equation, like we did before. There's my equation. Once I have my equation, I plug in 7. And number 19, find the limit as we go to 0 from the right side. Well, here's the right side, the numbers that are bigger than it. And if I look at this, it goes 13, 125, 1250. Well, there's no limit. It looks like it's going up unbounded. Now, if you look at it from this way, look at this, it's getting closer and closer and closer to 3. But this way it's not. So there's no limit on this side. This way there'd be a limit of 3. This way there's nothing. What does this look like? We spent quite a bit of time doing these Riemann sums. And this looks like I'm starting at -1 and I'm adding on some interval of 3 divided up by an infinite number of rectangles. So if I start at 1 and add on 3, I'm going to 2. And the function is just that number being squared. So on these problems, you're supposed to be able to look at this and know this right here. This is something squared, that's x squared, starting at -1 and adding on 3. -1 plus 3 gets you to 2. So I'm going from -1 to 2, and I'm at 3 there. All right, last one, find the average value over 4. Well, that's 1/4. Sorry, this should be 0 to 4. Did my math wrong here. And that's 4. And this is 4. And let's just check that with the calculator, make sure I did that one right. I'm just going to go math 9. And I'm going to go from 0 to 4 of the function 2x plus 2 dx. And there's 24. And should divide it by 4. The answer should be 6, not 16. Looks like I had it wrong there. So that's all we're doing. We're just integrating this function, which is right there from 0 to 4. And that's a range of 4. The answer should be 6, just what it says on your paper. I just wrote it down wrong there. All right, hope this helps. If you have any questions, please see me in class.